Okay, so the last video got cut just a little short, but we're gonna finish up Unit 2, which was the atomic structure and periodic table for our final review packet. So, identifying the total number of electrons that each sublevel can hold, we blocked them off on our periodic table, and we identified that the s orbitals can hold up to 2 electrons, and then once we fill those up, we enter the p sublevel that can hold up to 6. Again, 2 plus 6 gives us 8, which is those valence electrons. That's why we call the S and P main block, or the main blocks on the periodic table, because those are the electrons that we look at for our valence electrons there. So, fun fact, hello. And down here we have the Ds, which are the transition metals in that middle portion of our periodic table, and that starts with scandium as number 21. And in terms of making it through that through zinc, that is going to take care of 10 electrons. So that is our D block, and we know that the Ds are we said delayed because they actually entered the previous energy level based on the period numbers right there. So looking at gallium, for instance, we can use the electron configuration. We identify that gallium is number 31, which actually it ends up at the end of the 3D block. It's actually the first one in 4P. So because we know where it ends, we can then identify what should come before it, which is everything else in order. And what we do is we go in order. It's actually, we didn't specify this in class, but this is actually what's called the Aufbau principle, which is the idea of filling in lower energy subshells first, which is why we do write 4s before we do 3d10, and that actually, it also goes in correlation with the periodic table that way as well. So that's the way that we did it. That's the principle that we're going off of. But sometimes you might see the D, and I'll actually show you here in a second because it was typed this way on our review guide, but you'll see that the 3D comes after the 3P. That's just based on the physical energy level, based on it being in the third period. So those are just different ways, but we do the Ds after those S block orbitals or those subshells. So we enter the 4P1. It's the first one in there, and the abbreviated notation we identified as going through wherever our most recent P6 is, which is all of the noble gases. So the abbreviated is based on a noble gas. The noble gas that takes care or represents all of those electrons there is argon. And then we tack on whatever's left over. We have our 4s2, 3d10, and 4p1. How do we enter this? Well, we have to make sure that we have our electrons in each orbital paired up only when we need to, one up and one down. And then what we'll notice is we'll end up getting, of course, to 4p. And the good thing is, if you are comfortable with how to draw these orbital diagrams, then those will help you actually come up, as you can see, with the electron configuration up there, because you know that gallium has 31 electrons based on its proton amount. So you can fill in those arrows up until 21, and that's where you get to the 4p1 subshell there. So that's something that you can do if you find yourself stuck. Bohr diagrams, we identify a nucleus, of course, and more often than not, we'll give you a certain isotope of gallium or any other atom, and then be able to actually put how many protons and neutrons exist in that in that gallium nucleus or whatever it might be, whatever element. But for now, just for simplicity's sake, we're just going to say that this is a gallium nucleus, however many neutrons may be with those 31 protons. And then what we're also going to do is at our energy levels, which is based off of the period number that gallium is in. And so we find gallium in the fourth period, which then lets us know that there's actually going to be 4 energy levels where the electrons are going to exist around that gallium nucleus. Hello. Let's see if I can make a better line. There it is. And then one more. Right? That's not going to come out well, is it? Circles are hard. I need a compass. All right, there we go. Woo. So next up, needing to make sure that we put those electrons in the right spaces, and it starts to, you see how everything connects just as a different version of a representation of the atom of gallium there. So you can start to see that, because in the first energy level, there's only 2 electrons that can exist. Again, that represents hydrogen and helium. In our first period, we can only hold 2 electrons on that first energy level. And then we get to the 2, or the second energy level. The 2s is 2 electrons, and then the 2p contributes that same shell. So you actually end up having the 8 that we were talking about before, and there's 8 elements in the second period. So there's 8. Then we get into the 3s, and then so on and so forth. You start to see, there's 8 in the third level before we enter the fourth. So I'm going to put 8 here. And then we enter the fourth with the 4s2. So we're going to put those 2 here. You could draw as dots around them too as well. I'm just kind of simplifying it here. But then, of course, with the D sublevel, you see that we are going back and entering the third level once again with those 10 electrons. So those 10 electrons actually find themselves with the 8 from the s and the p orbitals for a total of 18 there. And then last but not least, that last lone electron in the p sublevel contributes to the fourth energy level. So if I were to ask you, hey, how many valence electrons does gallium have? Well, because these 10 went backwards into the third level, truly, gallium, just like aluminum, has only 3 valence electrons, and that also lets us know what ion charge it would form if we're to form an ion. So there is our Bohr diagram for that. The Lewis dot structure just goes off of those valence electrons, being able to note that there are 3, so there should be 3 dots around there. That is the simplified version of what this atom would look like. Why do atoms gain or lose or share electrons? Of course, it is to fulfill the octet rule. And then, of course, well, what is the octet rule? And it is the need for 8 valence electrons in the valence, and of course, again, valence means outermost shell. All right, and so based on whether or not these atoms have close to 8 electrons one way or another, they're either going to gain electrons to form ions, lose electrons to form ions, or they start to bond, which we're going to start to talk about next unit, in order to achieve the 8 valence electrons, which represents a full outer shell. What element is represented by the following configuration? So this is what I was talking about. This isn't necessarily incorrect, but I prefer, of course, for us to make sure that we put the D sublevel electrons in between the S and the P of that particular energy level. So in this case, it's the 3 in between the 4s and the 4p, just because that's the way that we had covered it in class. Again, if you were to look it up online, you would see it written as it is here, and that's just because certain ways are based on, you know, what somebody prefers to do. Again, we go through based off of the energy levels of the actual subshells. So you'll actually find D's after the S's for us. But either way, we really just need to know where this thing ends, and we see that it ends at 4p3. And so to identify what element that is, we see which one is 3 into the 4p sublevel, and we find that to be As, or arsenic. And then we can do the same thing here. We notice that the noble gas that represents a bunch of electrons is argon, which would actually be the same for up here if we wanted the noble gas version of the configuration for arsenic. But in this case, we are just focused really, again, on where does this thing end, because, of course, all of the electrons that come previous to it are accounted for. So 4s2, that is going to be on our group 2, all right, the alkaline earth metals, and 4s2 would be calcium. So hopefully the different visuals here for the electrons and these models show just how interconnected these things are, and how if you are stuck on, you know, the electron configuration or the orbital diagram or the Bohr model, like, you could use those to then help you out identifying what one should be if you don't know it. So that should help out, and I will see you in the next video.